Photodiodes are two-terminal semiconductor PN junction devices. They require reverse bias for their operation. Significant feature of these devices is that they convert light into electricity. One can see the operation of photodiodes. The functioning of photodiodes is exactly inverse to that of light emitting diodes. In LEDs, input is electricity, output is light, whereas in photodiodes, input is light and output is electricity. In LEDs, the functioning requires forward bias, whereas photodiodes require reverse bias for their functioning. The basic principle underlying the functioning of photodiodes is generation of electron hole pairs. An electron which is in a covalent bond, it is not free. To make it free, one needs to give certain amount of energy to it. Then it becomes free, leaving behind a hole. So energy given to a covalent bond electron generates a free electron and a hole. Both are current carriers. Their generation naturally increases carrier concentration and hence conductivity. More conductivity results in more current. So energy supplied to electrons, covalent bond electrons, leads to flow of more current in the device. In terms of energy band theory, the electrons which are in the valence band, they go to conduction band when certain amount of energy which is at least equal to band gap energy of the semiconductor material used for the fabrication of the device. When this energy is supplied, electron moves from valency band to conduction band. Electron in conduction band means free electron, more electron concentration. More electron concentration means more conductivity. More conductivity means more current. But This more current, its origin, its source is the energy supplied to the valence band electron. In case of photodiodes, the required energy for the electron to become free electron or conduction band electron, it is supplied through the incidence of light. Light is associated with energy. This energy is given by Planck's law. It is equal to h nu or hf. F is frequency of the light. These diodes, photodiodes, find several applications ranging from production line counting systems to receivers of the optic fiber communication systems. Special diodes, photodiodes, series on semiconductor devices and circuits, lecture number 2.24. Photodiodes are PN junction diodes. They are semiconductor diodes. They take light as input and they give electrical current as output. Hence, they convert light into current. They are used to detect light or presence of light. It can be seen their operation is inverse to the operation of LEDs, that is light emitting diodes. With this small introduction, we now enter into a session, a video session, in which we focus our discussion on photodiodes. Let us move now further and start the core session. A few points regarding the principle of functioning of photodiodes. Photodiodes are, as already mentioned, semiconductor diodes, PN junction diodes, whose operation is inverse, exactly inverse to that of LEDs, light emitting diodes. Photodiodes convert light or optical signal energy into electrical current or power. LEDs convert electrical current into light, whereas photodiodes convert light into electrical current. Hence, photodiodes, LEDs, their operation is inverse to each other. For the generation of EHP, electron hole pair, energy in the form of light is given to valence band electrons. To flow current through the diode, electron hole pairs require to be generated. For their generation, certain energy is required. The energy in photodiodes, the necessary energy to create electron hole pairs in photodiodes it is given in the form of light, and this energy excites valency band electrons into conduction band, producing electron hole pairs. The energy of the incident light, it is given by E equal to hf. E stands for energy, h stands for Planck's constant, f stands for frequency of the light. This relation is according to Planck's law, or this is actually Planck's law. So the energy of the incident light should be at least equal to band gap energy of the semiconductor. This is an important aspect. All light or any type of light or light of any frequency cannot work with the photodiodes. Only light whose energy is at least equal to band gap energy, they only can make the photodiode operate or work by exciting valency band electrons, by generating electric current from light. Now we consider the symbol and functioning of photodiode. Here we can see the symbol. It is the symbol of ordinary diode with a small modification. Two arrows are included in the symbol of ordinary diode. We can see these arrows indicate light from outside falling over the diode. One can notice the similarity between symbols of photodiode and LED. In LEDs also, there are two arrows, but their arrows are pointing outwards, away from the diode. Here in photodiode symbol, arrows indicate direction of arrows is towards the diode. When it comes to functioning of photodiode, it is always operated under reverse biased condition, and the diode is enclosed within a plastic case. Usually all sides of the plastic case, they are covered with only a small opening somewhere here on one side, through which only light can enter and fall over the diode. A small opening. The light incidence is arranged such that it is on a region near to the junction somewhere here. Some more points regarding photodiodes. Many of the photodiodes use pin junction rather than a PN junction to increase speed of response. What is pin? P stands for P-type, N stands for N-type semiconductor, I stands for intrinsic. Whereas PN junction means ordinary PN junction, one side P, another side N. Pin junction means one side P, other side N. In the middle, intrinsic material. Because of their greater band gap, silicon-based photodiodes generate less noise than germanium-based photodiodes. Naturally, silicon is preferred. The wavelength range over which different semiconductors work as photodiodes, they are given here. In case of silicon, light with the wavelength range 190 to 110 nanometers. For germanium, it is 400 to 1700 nanometers. Indium gallium arsenide. For this material, it is 800 to 2600 nanometers. Lead sulfide, it is 100 to 3500 nanometers. These are wavelength ranges of the incident light for the functioning of Photodiodes. The volt ampere characteristic of photodiode, it is given by I. I stands for current. It is equal to Is plus I naught into 1 minus e power v by eta Vt. Notice the second component, which is adding to Is. This component is current in the ordinary diode in reverse direction. When the diode is under reverse bias, it is added to Is to give current in the photodiode. Here Is is short circuit current and I naught is reverse saturation current. Notice the current I is in reverse direction, means it is flowing from N to P in the diode. Photocurrent, the current Is, which is designated as short circuit current in the reverse biased junction diode, which is a result of light incidence, is called photocurrent. Is is a short circuit current. It is actually photocurrent. It is called so because it is due to the incidence of light over the diode. Note that the light falling over the junction is acting as minority carrier generator or injector. The generator carriers then diffuse to the junction, cross it, resulting in the photocurrent. Some important points regarding the functioning of photodiodes. Photocurrent, it depends upon the intensity and frequency of the incident radiation. The yield of diode varies with intensity even when frequency is maintained constant. In addition, a given intensity of light at one frequency gives different number of minority carriers from an equal intensity of light of another frequency. So the important point, basic point regarding photocurrent is that intensity of the radiation, frequency of the radiation. These two are important aspects of the radiation which influence the amount of photocurrent. Location of light focus. The light spot is within a distance of diffusion length from the junction. The light spot is required within a distance of diffusion length from the junction. The current depends upon distance of light spot from the junction. The current is due to diffusion of minority carriers to the junction, and if the focused light spot is far away from the junction, the generated minority carriers can recombine before diffusing to the junction, resulting in a smaller current. Note, in LEDs, the light emission is in and around the junction region. Photodiode operation is inverse of the functioning of LED. It takes light and generates electrical current. That is the meaning of inverse operation relation between LED and photodiode. But as far as activity is concerned, generation of light, emission of light, or acceptance of light by photodiode. Generation of light by LED, acceptance of light by photodiode. These two happens in both the diodes. The activity happens at or near the junction region. In case of photodiodes, the light must fall within a distance of diffusion length from the junction for its effective performance. Here is shown a graph indicating sensitivity of a photodiode as function of distance of light spot from the junction. You see, when the light spot is near the junction, amount of current is maximum. When the spot is moving away from the junction, the amount of current is falling on N side. It is also falling on P side. As the spot moves away, current is falling, it moves away in N side, also it is falling away. Ln stands for diffusion length of electrons, Lp stands for diffusion length of holes. Another parameter, we already encountered photocurrent, now we consider dark current. What is dark current? The current in the diode, photodiode, in the absence of illumination is called dark current. It is due to the reverse saturation current of the diode as well as the current due to the carriers generated by the background illumination. The dark current corresponds mainly to the reverse saturation current due to thermally generated minority carriers. Notice what is photodiode? It is a diode, ordinary diode, PN junction diode, biased in reverse direction. Now, let us suppose there is no light, nothing. Then in such case, certain amount of current flows. That current is dark current. When light falls over the diode, minority carriers get generated. It results a certain amount of current. That current is photocurrent. That's all. Ideas are quite simple. Now, some important points regarding the radiation or light that falls on the photodiode. Maximum allowed wavelength. This wavelength corresponds to the minimum frequency required for the incident radiation. Energy of the illumination depends upon its frequency wavelength. If the wavelength is more than certain value, then incident radiation cannot generate current because its energy is insufficient, less than band gap energy of the material. The maximum allowed wavelength of the incident radiation depends upon band gap energy of the semiconductor used for the diode. The relation between wavelength of the incident radiation and band gap energy of the semiconductor, that relation is lambda equal to 1.24 by Eg. The important point regarding photodiodes is that the incident radiation should have certain minimum frequency. It should be of certain minimum frequency. If frequency is less than that minimum, then it cannot generate current in the diode. The minimum frequency of the incident radiation, it is related to band gap of the semiconductor, band gap energy of the semiconductor material with which the photodiode is fabricated. That relation is given by lambda wavelength is equal to 1.24 Eg. Here lambda is maximum allowed wavelength. The wavelength of the incident radiation should not be more than this. If it is more, then it cannot excite current in the diode. Some points regarding performance indices of photodiodes. There are three critical parameters in case of photodiode performance. One is dark current, another is responsivity, third one is response speed. What are these parameters? What is their significance. Out of the three, one is already introduced. Remaining two, here we talk about. A good photodiode should have a zero dark current, or it should be extremely small as compared to photocurrent, corresponding to the minimum level of illumination. So dark current should be as low as possible. So from observing the amount of dark current, one can have certain understanding regarding the performance of a photodiode. If it is large, then there is very little possibility for it to be a good photodiode. Another parameter is responsivity. The responsivity of a photodiode is defined as the ratio of generated photocurrent and the incident optical power. So output is generated photocurrent, input is incident optical power. Ratio of output to input is responsivity. Ideally, it should have a value equal to 1 by Eg, Eg in electron volts, but the practical diodes exhibit less value, recombination being the cause of this reduction. Another performance index is response speed. The speed of the photodiode is governed by how fast the photo-generated carriers can be collected by external circuit. It can be approximated with transit time TRR given by W by Vd. Here W is width of transition region, Vd is carrier drift velocity. So faster response requires small width of transition region, but it can be shown that larger photocurrents require wider transition regions. Some more points regarding the diodes, photodiodes. What materials are used for their fabrication? At lower frequencies, lead sulfide is generally used. When incident wavelength is beyond 1 micrometer all the way to about 3.5 micrometers. Even though silicon cannot be used for LEDs, it can be used for photodiodes. Effectively, for a wide range of incident wavelengths from 190 nanometers to 1100 nanometers at the higher end of the spectrum. Applications. The PN photodiode find extensive applications in high-speed reading of computer punched cards and tapes, light detection systems, reading film soundtrack, light-operated switches, production line counting objects which interrupt a light beam, etc. Now we enter into a discussion about a kind of photodiodes. These are called avalanche photodiodes. A few points regarding avalanche photodiodes. Avalanche photodiodes or EPDs, in short, are variants of photodiodes. The generation of carriers is as in photodiodes, but in these diodes, the carriers get multiplied, thereby giving more output current for a given input illumination. Avalanche refers to multiplication. Generation of carriers principle is same as in ordinary photodiodes, but after generation, avalanche multiplication happens, resulting in more current. They are operated under a large reverse bias conditions where electron hole pairs generated by incident illumination get avalanche multiplied by impact ionization. The diode consists of a transition region from which the photo-generated carriers drift into a high electric field region called avalanche region. The drifted carriers then gain enough kinetic energy in this region to ionize the bound electrons of the host atoms by collision. Structurally, it is of P plus. I stands for intrinsic. P N plus. Plus means more concentration, where N plus layer is used as substrate. The structure is commonly referred to as P plus pi P N plus, reach through structure, and photodiode is called reach through avalanche photodiode. Rapid. wrapped RAPD. The optical power is coupled into the device through P plus layer, which is made to be very thin so that most of the optical power can enter into Pi layer. Photo detector like APD or pin diode. Pin diode means P stands for P-type material, I stands for intrinsic, N stands for N-type. A diode can be made with this kind of structure also. P one side, N one side, in between intrinsic material. That type of diodes are also available. A photodetector is usually characterized by two important parameters: quantum efficiency and responsivity. The first one is defined as number of electron-hole pairs generated per incident photon. It is given by number of electron-hole pairs divided by number of incident photons. IPH by E by P naught by HC by lambda. Here IPH is average photocurrent generated due to average incident optical power P naught on the photodetector. In practical photodiodes, it varies from 30% to 95%. The second important characteristic parameter is responsivity, or which is defined as photocurrent generated per unit incident optical power. This can be described as IPH to P naught ratio, which is equal to E lambda eta by HC. These are being widely used as optical detectors, devices used to convert the optical information emerged from the fiber and into equivalent electrical signal at the optical communication receiver. Now, photodiodes, they are used in optic fiber communications like LEDs. LEDs are used at the transmitter end, whereas photodiodes are used at the receiver side. Photodiodes, what do? They accept light from the fiber and convert it into electrical current, electrical signal. This current is then taken for further processing to get back the signal that is transmitted from the other side. With this, we come to the end of the session. Before closing down, let us recollect important points, aspects that are touched upon in the session. Photodiode is introduced, its structural features, its VI characteristic, materials used for their fabrication, applications, and a class of photodiodes, avalanche photodiodes, and their operation, and also several other aspects pertaining to photodiodes. They are all covered in this session. Hope this session is useful to you. We meet again soon in another session with a new topic.